All right, so it's time to learn how we can run CCDC for a larger area. And this is what is being shown in the second checkpoint B of the chapter. So this script is very short. I'm going to try to maximize it here, and I'm going to run it to clear the inspector on the console. And so what is happening in this script? First of all, we are loading this set of utilities that we develop at VU to interact with CCDC. I want to emphasize that we have developed these utilities mostly for our own research purposes at VU, and we hope that they can be of use for other people. That said, these are not in any way the official way of using CCDC or the sanctioned way of using CCDC. They're just one way of dealing with time series and a way of interacting with the results of CCDC. In this case, I need to load those utilities because they will allow me to create a Landsat collection very easily without having to do it all from scratch. And so we will see that in a second. I am defining a study region here, which is also a place in Brazil where we, close to where we were looking at the time series. And what I'm doing down here is I want to specify when I want to extract the time series, what is the time range for which I want to extract the time series. So I want to do that between the year 2000 and 2020, in this particular case. And I want to run CCDC with this spectral bands. Now, what the bands that you specify here, they could be any bands in your stack. Let's say that you're going to have a stack of vegetation indices. Then you could create a stack of vegetation indices, time series of vegetation indices, and then use those vegetation indices to run CCDC. But in this particular case, we're going to keep it simple. We're just going to do it with the original input spectral bands. And this is where we started using the utilities that I mentioned. So one of the functions in these utilities, it's called get Landsat. And so what this function is allowing us to do is, instead of having to call Landsat 4, Landsat 5, Landsat 7, Landsat 8 collections, and then have to manually filter for low clouds and low noise and et cetera, we build this function to do it automatically so that we don't have to think about it too much. And so what this function takes is a dictionary with a set of parameters. In this particular case, we're just telling it we want it to be collection 2. Then we are filtering that collection of Landsat images to be only for the area where we have our study region defined. We are also filtering it so that it's only between the start and the end date that we defined previously in lines 16 and 17. And then we're telling it give us only the bands that we are requesting, which are the bands that we define here in line 18. And so after we do that, we are going to obtain this collection called filtered Landsat. And this line is printing the first element of that collection. So that is going to be right here. And it's telling us you have these different bands, they're even named. And these are the properties of the image, which are simply the properties that come attached to any of the surface reflectance bands from the Landsat collections. After that, what we're going to do is to define how we want to run CCDC. And so if I go to the documentation here on the left, and I look for CCDC, I retrieve the function, and it tells me these are all the arguments that you want to specify. And so we could leave a few of those to be the defaults, but just to be clear, even if they're the defaults, we're going to define them manually, even if it's to be the defaults, just to be very clear how things are being run. And so the first thing that CCDC requires is which bands are going to be used as the breakpoints. So what bands are going to be used for the change detection process. And so in this particular case, you see that it's almost all of the bands except the blue band. And that is because the blue band is usually a little noisy. And so if we include the blue band as a breakpoint detection band, it could trigger changes that we don't want, changes that are really not what we're trying to capture. So we typically avoid using that one. The second option is the T-mask bands. So I mentioned that there is a cloud detection algorithm that happens inside CCDC. And so if you don't specify any bands, this T-mask procedure is not applied. In this case, I specified the green and the square 2. Really, this should be square 1. But in this particular case, it really doesn't make much of a difference. But this should be really be square 1, which is now correct here in the documentation. Minimum observations, chi-square probability, minimum number of years scalar, we're going to leave those as the defaults. They work pretty well. We're not going to deal with that. The next parameter that we need to specify is date format. So once CCDC runs, it's going to give us the breaks and the lengths of the segments. We need them to be in some unit of time. And the function tells us it could be Julian days, it could be fractional years, it could be Unix time in milliseconds. So they all have their pros and cons if you're working with them directly. But we typically use fractional years because it's the easiest one to conceptually understand. And you're going to see that in a little while when we start playing with the outputs of the algorithm. So we're using 1, which represents fractional years. And then for the lambda value, you see that the default is 20. And so the default is 20 because originally the surface reflectance bands come scaled by 10,000, but this function that we're using to retrieve the Landsat collections, this is already giving us the collection in surface reflectance units that go from 0 to 1. And so therefore, we cannot use the default value of 20. We are scaling that by 10,000. So that's why the value of lambda here is 0.002. Finally, there is this option here that says maximum iterations, and the default is 25,000. So this is kind of the traditional way of running CCDC, is to specify a number here to run the regression the way that we want. However, 25,000 is a very high number, and this means that the process of running CCDC might take a long time if we use a value of 25,000. So we usually settle for a little less than that, So only 10,000 iterations should be enough. And that's what we're specifying here. And of course, the more essential parameter that CCDC requires is the collection itself. So I am calling it here collection and passing it the Landsat collection that we just created previously. And so what I'm doing here is that I'm defining a dictionary of the parameters that I want to use to run CCDC. Once they're defined, I can use them here and pass that dictionary to the CCDC function to tell it how we want it to run. And we are assigning the results to this variable called CCD results, and we're printing those results. And so that is this image that you see right here. And so remember that the way that our engine works, this can print all the bands that this is retrieving. We are not loading them in the map. They probably wouldn't even load in the map. And that's because CCDC is highly computationally intensive. And so you typically want to run the algorithm, export the results, and then look at the results after they have been saved. And so I'm going to skip the bands for 1 second, just to clarify what I'm telling you about exporting the results. You see that in this particular script, this variable called export results is set to false. And that's because we are not going to re-export CCDC for this particular case. I already exported it, and then we're going to load it in the next checkpoint. But this is showing you how you would export the CCDC results. And it's also showing you that we are creating a dictionary here that is called metadata that contains all the parameters that we use to run CCDC. And that's important because once we load those CCDC results, we want to remember how we run them, where they come from, what time range they cover. And so one way to do that is just to create this metadata, including everything that we use to run CCDC. And then we set that metadata to the output images, to the output image, so that we can recall how things were run. All right, so the second thing I want to say about this is that I want to emphasize that running CCDC for large areas or medium-sized areas is very computationally intensive. And so if you want to learn how it works, you should always start looking at individual pixels. If you want to use the tool that I showed you before, if you want to use it for a larger area, always test it in a much smaller area, the size, say, of a city, the size of a few square kilometers, to get a sense of what it looks like. And then after you get a graph of how it works, if needed, then you can start running this for larger areas. All right, last thing I'm going to say for this checkpoint is that I'm going to show you how the outputs of CCDC look like, how the bands look for the results. And so remember that we assign the results to this variable, and we're printing the results. So that's what we're seeing right here. And so the outputs of CCDC is an image with 23 bands, but these are not your typical bands. They are array images, and some of them have 1 dimension and some of them have 2 dimensions. We're going to look at that later, but you can even see that here. It's in the name of the band. And so the way that this is organized is that it's giving you all the bands with T start, which is when the time segment starts, T end, which is when the time segments end, T break, so the date when CCDC is detecting that break. Number of observations is telling you for a given segment, how many observations went into that segment being fit. change probability is corresponding with timing of break, and it's telling you what is the probability of change that the algorithm observed. This is typically going to be either 1 or a number close to 1. If you want to restrict the changes only to the most likely breaks, you select the places with probability equal to 1. After this, you see that we have all of the bands that we told it to use at the beginning. So all of the bands that we define as inputs, we're going to have them here, and we're going to have the coefficients. So blue, coefficients, green, coefficients, red, coefficients, near infrared, first shortwave infrared, and second shortwave infrared. And so these coefficients include the intercept, so the place in the y-axis where the segment will intersect the y-axis, or the reflectance, or the value at which each segment will intersect the y-axis. Includes the slope, which is basically the inclination of the segment, and includes the harmonic terms. So that's going to be the pairs of sine and cosine terms. And this is using up to 3 pairs of those. After that, you're going to have the same thing. And so we're going to have the root mean square error for each of the segments, for each of the input spectral bands that we define, from blue to the square 2. And lastly, you're going to have the magnitude of each of the breaks, and you're going to have that also for each of the bands. So as you can see, we're getting a lot of information and a lot of data out of the CCDC results. So we assume that we run this, we have a data set that is pre-saved, and that's what we're going to use for the next checkpoint. So I'm going to close this, and I'm going to stop for a second before I move to the next checkpoint.